Welcome everyone. Today is the fifth tutorial session in the course Structural Analysis-1. Um, I am Sukanya Karmakar. I am a second year PhD student in the Department of Civil Engineering at IIT Kanpur. So, this is my email ID as displayed in the slide. If there are any doubts, you can also write to me. So today I'll be mainly covering uh, the concept of the conjugate beam method. In the last week, we had covered the moment area method. So these methods are basically used to calculate deflection and slope in beams, and they can also be used in frames. But for frames today, I'll be using the unit load method, which was covered in the last to last week material. So, um, I'm starting off with uh, conjugate beam method. I'll try to explain the method with questions, and then we'll move to the unit load method. And I have already demonstrated the use of unit load method uh, the use of unit load method in calculating the deflection in and the deflection slope. Basically, its application in beams. We have already covered that, but today I'll be using the unit load method in calculating deflections and slopes in uh, frames. So this is the first question. A beam is given and we have to draw its conjugate beam. So uh, the basic concepts in a conjugate beam is that the load, suppose a beam 1 is given and we have to draw its conjugate beam. So on the conjugate beam, the load will be equal to the uh, curvature of the original beam. And in this beam, no loads have been specified. So basically, this question is trying to understand uh, how will you draw the conjugate beam in terms of the supports. Uh, we know that in a real beam, uh, at a fixed support, there will be uh, bending moment, there will and shear. So in the conjugate beam, it should be a free end, because in a free end, uh, sorry. Okay, let's start with a different question. Then I'll move to this question. Suppose this is the question. First, let me explain it through a question, then we'll move on to that question. So, this question tells that we have to determine the slope of the beam at point A. This is point A. This is point B. We have to determine the slope of the beam at point A, and E and I have been given. So, to apply the conjugate beam method, first we'll have to construct the conjugate beam, and the load on the conjugate beam is equal to the M by EI diagram or the curvature. So, first I'll construct the M by EI diagram. For calculating the bending moment diagram, I first need the support reactions. So here, first I'm calculating the support reactions. So this loading is It's straightforward. If there is a moment of 50 kilonewton meter, then the reactions will be 50 divided by the length of the beam, that is 8 meter. So this being the beam, if a load of 50 kilonewton meter is acting in the clockwise direction, then the resisting moment should be in the anti-clockwise direction, and is equal to 50 divided by 8, which is 6.25 kilonewton, and even this is 6.25 kilonewton. And from here we'll be drawing the M by EI diagram, and I am drawing the bending moment diagram on the compression side. So this reaction of 6.25 kilonewton, it is pulling the support down. So a tension is on the, this is the tension side of the beam, and this is the compression side of the beam. So here the moment will be like this, bending moment diagram will be like this, and this will be like this, and this will be like this. These are all straight lines because your moment equation will be, what will be the moment equation? It will be, if I take x from this direction, it will simply be 6.25x with the negative sign. So the moment equation being 6.25x, what will be its value at 4 meter? It will be 6.25. So it will be 25 kilonewton meter. So here the value is 25, and even here the value is 25. This being a negative sign, this being a positive value. And in this beam, the value of EI is constant. So we can simply divide it by EI throughout the beam. It has the same EI. So we have the M by EI diagram. Now this M by EI diagram will be the load on the conjugate beam. So in the conjugate beam, pinned support will remain pin and roller will remain roller. And this M by EI diagram will be the load on the conjugate beam. So positive bending moment diagram is downward load, and negative bending moment is upward load. And okay, now we'll have to, what is required, we have to calculate the slope at the slope of the beam at point A. So we know that when we are required to calculate the slope at a point, it is equal to the shear force of that same point in the conjugate beam. So if I can find the shear force at point A in the beam, we can calculate the slope at point A in the actual beam. So slope at point A for the real beam, is equal to shear at point A in the conjugate beam. This is the conjugate beam and this is the real beam. So for calculating the shear at point A, I need the support reaction because that is the shear at point A. So for this, you need to calculate RA. How will you calculate RA? Simply take moment about point B. So taking moment about point B is equal to 0. So RA into 8. This length is 8 meters. So this is 4 meters, this is 4 meters into 8 plus I am taking clockwise moment to be positive. So RA into 8 in the clockwise direction plus half into base is 4 meters into height 25 by EI plus plus the lever arm 4 plus we take 4 into 1/3. Okay, minus this is the now I have written the expression for this triangle. Now I will be writing the expression for this triangle. For this triangle it will be, so this load is acting in the downward direction, so it is creating about point B, it is creating a anti-clockwise movement. So that will be minus half into 4 into 25 by EI and the lever arm is 2/3 into 4. So this is equal to 0. So now I solve this and get the value of RA. RA into 8 plus 800 by EI minus 400 by EI by, sorry, here a 3 will appear, okay, here one 3 will appear. Okay. So from here RA is equal to this is 400 divided by 3. So this is the value of RA, and from this diagram we can predict its deflected shape. This moment is pushing this side of the beam down, so it will go like this, and this side will move up. So we consider rotation in the clockwise direction to be positive, and here theta is in the anti-clockwise direction and we get a negative value of the shear. So this clears the sign. Why is this negative sign coming up? And this is we should be getting a negative sign, which is clear from the deflected shape of the beam. So plugging in the values, theta is equal to theta at point A will be equal to 50 by 3 EI. Now I am dropping the negative sign. We know theta is in the anticlockwise direction. So with proper units, 3, E is given in given as 200 GPa. So let's put it as in the units of Newton per meter square. So it will be 200 into 10 to the power 9 Newton per meter square. 8 into 10 to the power 6 is I in to the power 4. So to convert it into meter to the power 4, I have multiplied it with this factor. Multiplied with, while calculating this RA, the load was put in kilonewton. So I need a factor of 10 to the power 3. So when you simplify it, you get theta to be 0.01 radian. And this theta is in anti-clockwise direction. So I hope this question is clear. Is there any doubt in this question? Okay. If there is any doubts, we can take them up at the end of the session. So this question is done. Moving on to this question. So this question tells, this is not related to conjugate beam method. This is only, by this question, I want you to develop a sense of the bending moment diagram. Like seeing the bending moment diagram, you should be able to predict the position of the supports and what kind of load is acting on the structure. So to understand that concept, I have put this question. So this is the bending moment diagram. This is the bending moment diagram. And out of these 4 options, you'll have to select the beam which corresponds to this bending moment diagram. So yes, D is the right answer. So let's go through the options one by one and we'll try to understand why D is the correct answer. So for this question, how will this beam deflect? It will deflect like this. And here we can see that at this end, at this end, there is a pin support. So there is no bending moment diagram. But in the given question, I had drawn wrong options. Nobody pointed it out. Still, you told D is the right answer. Actually, none of them should have been the right answer. So now D is the correct option. Okay. So as I was explaining, this is a pin support. So here there is no bending moment diagram, but in the given bending moment diagram, there is a moment. So this cannot be the right option. And okay, now moving on, and also at this support, here bending moment, there will be a moment, and here the moment is 0. So with the same logic, here there will be certain moment, but in the given question there is 0 bending moment diagram. So even B can't be the option. So A can't be the answer, B can't be the answer. So for this, how will this, for C, uh, again this end, this is a free end. So the bending moment diagram will be 0. So the bending moment diagram here will be 0. Yes, the beam is overhanged at one end. Yes, that is fine. But here the bending moment diagram is the moment is 0 at the free end, and here you have a certain value of moment. So even this can't be the answer. And this for this makes sense. A concentrated moment is given, and here bending moment is there, and here there is a uniformly distributed load. And how will this deflect? This will deflect like you're pushing it up, so it will move like this. So at this end the moment is 0, the moment is 0. Here this be UDL load is there. So since the load is UDL, the bending moment diagram will be quadratic of degree 2, and here we have a quadratic curve, and at the free end there bending moment is there, and we have a concentrated moment here. So this is the right answer. So the solution is D. Okay. So this question is clear. So moving to the next question. This is the same structure as we had encountered earlier. So in this question, you will have to calculate the maximum displacement in the beam. So uh, what do you understand by maximum displacement? Like the, and I want you to use the concept of conjugate beam. So displacement in real beam is equal to the bending moment diagram in the conjugate beam. You want the displacement to be maximum in the real beam. So the bending moment diagram in the conjugate beam, the moment in the conjugate beam should be maximum. When the moment in the conjugate, when is the moment maximum? We know that when the moment is maximum, at that point the shear force is 0, because we know that the derivative of bending moment is equal to shear force. So we will have to find a point in the conjugate beam where the shear force is 0. Then once the point is determined, when we can calculate the moment at in the conjugate being the moment at that particular point, and once we get the bending moment at that point, that will be equal to the displacement in the real beam. So from the last question, uh, we know the M by EI diagram. The M by EI diagram is known. So this is the M by EI diagram. So let's redraw it. So this is the M by EI diagram. This value is 25 by EI, and we had also already calculated the support reactions. This is the conjugate beam. I'm removing the supports and I'm writing the reactions. This reaction was 50 by 3 EI, and this support was 50 by 3 EI. This being point A, this being NP. Now we have to find a point in the beam where the shear is 0. So let me cut a section here and I'm taking X from this direction. So let's draw the free body diagram for this left hand portion. So take this portion. Here it is 50 by 3 EI. Shear force is V. Moment is M. And see, from this triangle, we see that from this triangle, it is clear that when this height is from similarity of triangle, we can write this 25 by EI over a length of 4 is equal to, let that height be W dash over height of X. So here the load value will be 24x by 4 EI. Now we can write down we can sum the forces in the vertical direction to calculate the shear force. So V plus, so let's follow the sign convention, minus V minus 50 by 3 EI, forces are in the downward direction, plus half into height is this much, base is X. So as I had already explained, maximum displacement in the real beam, so will be equal to the maximum bending moment in the conjugate beam. And how will you get the position of maximum bending moment? That will be equal to the point where the shear force is 0. So I'm writing down this fact that maximum displacement in the real beam. So this support reaction has been calculated from this question. See this question number 3. This support reaction was here. This is, see, this structure in question number 3 and question number 4, which we are currently doing, is the same. Here in this was the conjugate beam, and in the conjugate beam you had calculated the support reactions, where RA was calculated to be 50 by 3 EI in the downward direction, and here I had assumed RA in the vertically upward direction. So basically the reaction is downward, in the downward direction the value is equal to 50 by 3 EI. So from there, in the current question, this is the support reactions appear from there, 50 by 3 EI, 50 by 3 EI. And one more doubt is from where I am getting 25 by EI. This value was already calculated in the previous question. This is from the real beam. You draw the M by EI diagram, which will become the load on the conjugate beam. So this, when this M by EI diagram was drawn, how was this M by EI diagram drawn? This is the given structure with the moment. You calculate the support reactions, and from here you construct the bending moment diagram. And since EI is constant in this beam, you can simply divide the bending moment diagram with that value. So from there you get the value 25 by EI. So I hope these values are clear. The structure is same in both the questions. In the earlier question, you had to calculate the slope at the point A at the left hand support, and in the present question, you have to calculate the maximum displacement. So maximum displacement in the real beam is equal to maximum bending moment in the sorry in the conjugate beam. And how will you calculate the position of maximum bending moment? See, so position of maximum bending moment. For that, you use the fact that dm by dx is equal to v. So bending moment will, the point where the bending moment is maximum, at that point the shear force is 0. Therefore, M is maximum where v is equal to 0. So in this equation, let me put this to be in equation number 1. Here you put v is equal to 0. So let's rewrite this equation. So in this equation, put v is equal to 0. So here v is equal to 0. So 50 by 3 EI is equal to 25 divided by 8 x square by EI. So from here, x is equal to 4 by root 3. Okay, so this is the point where bending moment will be maximum. Now, from this diagram, you will have to write the moment equation. So what is the moment equation? M is equal to this load 50 by 3 AI being in the downward direction, it's creating a hogging moment. So 50 by 3 EI into X, the triangular load UVL being in the vertically upward direction creates a sagging moment. So 20, so half into height is 25x by 4 EI into base, again it's x, so x squared into x by 3. So let's write it in a simplified form. So 50 by 3 EI into x plus 25 x cube by 24 EI. So now in this equation, simply put x is equal to this value which you had obtained. At that point, the bending moment will be maximum. So putting x is equal to 4 by root 3. So m will be equal to minus 200 by 3 root 3 EI plus 25 by 24 into 16 into 4 by 3 root 3. So when you simplify, you'll come up with a number 400 by 4 root 3 EI. And what does this negative sign mean? This negative sign means that uh, the maximum deflection will be in the downward direction. And this bending moment diagram is applicable, this bending moment equation which we derived is applicable in this part. So is applicable to this. Sorry, I'll like to correct myself. This, what is the, let's draw the deflected shape. This is the moment in the clockwise direction. So the beam will deflect like this. So maximum deflection, here the deflection is taking place in this direction. So it is in the vertically upward direction. And this will be value, or this is the bending moment in the conjugate beam. This will be equal to the deflection in the real beam. So deflection delta is equal to, just plug in the values, 400 by 4 root 3 into 200 into 10 to the power 9 into 8 into 10 to the power 6 into 10 to the power minus 12. Now everything is in meters. So in meters it is 0.016 meter, or in mm it is 16 mm. So this is the deflection of the beam. So I hope this question is clear. Now let's do this question. So we know that in a real beam, when it is fixed in the conjugate beam, we convert that fixed support into free, because we know that the shear force in a real beam, so we know that in a real beam, and let me write conjugate beam. So the load in real beam is related to the curvature in conjugate beam, the shear, or the other way around. I should have written the shear in conjugate beam is equal to the slope in real beam. The deflection in real beam is equal to the moment in conjugate beam, and the load in conjugate beam is nothing but the curvature of real beam. So in order to maintain, like, let's think in in terms of free end. Suppose in real beam it is a free end. So at the free end there should be slope and there should be deflection. So uh, it can't be in the conjugate beam, it can't be a free end. It should be a fixed end, because then only the shear and moment will appear. That is why. So let me draw it in terms of a table. In a real beam, if the end is free, in the conjugate beam, it should be fixed, because as I explained, in the real beam, in the free end, if there is theta and slope, in the conjugate beam, there should be shear and moment. So for shear and moment to exist, it should be a fixed beam. It can't be a free end. So in the real beam, suppose it is a fixed end. So at a fixed end, there is no slope and there is no deflection. So there should be no shear and no moment. When is this possible? No shear and no moment when it's a free end. So it is a free end in conjugate beam. Similarly, when it is a roller, in a roller, sorry, not roller, This is an internal hinge. In the internal hinge, at that point, the bending moment uh, in the real beam uh, at an internal hinge. So their uh, slope exists, deflection exists, but it can't be a roller in the conjugate beam because it can't be a internal hinge. I'm very sorry. It can't be a internal hinge in the conjugate beam because in internal hinge, the bending moment diagram is zero. The bending moment is zero at the internal hinge. So it should be treated as a roller. And vice versa, if it is an internal roller, it should be treated as an internal hinge. So I'm writing this. This is an internal roller and this is a hinge. So keeping these points in mind, what should be the conjugate beam of this real beam? So this is the real beam. Its conjugate beam will be simply this fixed end will be a free end. Why it is a free end? I've explained the logic here. This should be a free end. This is an internal hinge. It will become a roller. This is a pin support. It will remain a pin support, or it is basically it will you can treat it as a roller. So that will become an internal hinge, and fixed end internal hinge in real is equal to pin, or you can treat it as a roller, and free end will be a fixed support. Internal hinge in real is equal to roller support in conjugate. So this is a basic understanding of supports in real beam and conjugate beam. This is the okay. Uh, okay, it's given in certain books. Okay, as far as okay, I will look into this and I'll clarify it in the next week. I think so. It should be a roller, but I will clarify and I'll try to get deeper into this. This is a conjugate. So this question is done. So let's move on to this question. So, so in this question, again, I want you to use the conjugate beam method, but now I want you to calculate the deflection at point B, and B is an internal hinge and EI is constant. So uh, that is mentioned. So first you will have to calculate the support reactions, and from the support reactions you will have to calculate the bending moment diagram. So can someone calculate the support reactions for me and tell me the values? Because that is that has been covered in the first week, and by this time you should have been you should be very comfortable with it. So even I'm calculating it. So do it on your own, calculate the support reactions, and write in the chat box what would be the support reaction at A and C. At A, you will have two support reactions, the moment and the vertical reaction, and at C, you will have one support reaction. So let this be a roller. And at support A, the horizontal reaction will be 0 because no horizontal load is acting on the structure. So I'll give you about 2-3 minutes. Then I'll start solving the question. So take the portion BCD. So at B, the at B is an internal hinge. So moment is 0. So only there will be a shear Vy. So I'll take the moment about point B. So the contribution of By will disappear. Simply, okay, two of you have answered and have given me completely different answers. So I'll start solving it. So Cy into this distance is 2 meter, this is 2 meter. So Cy into 2 is equal to how much is this load? This is 20 kilonewton per meter. So it is 20 into 4 into 2. So from here, Cy is 80 kilonewton. Cy, okay, someone has answered 80 kilonewton. So Cy is 80 kilonewton. Then summation of Fy is equal to 0. So it's not required. Now take the overall structure and there take moment about point A. Summation of A is equal to 0. So clockwise moment is taken as positive. So MA plus 120 into 3 minus 80 into 4 is equal to 0. So MA is equal to 320 minus 360 is equal to 40, minus 40 kilonewton meter. Okay, this also someone has written 40 and 80, but you should have given me 3 support reactions. You have only written the numbers 40 and 80. So how do I understand you're talking about which values? So MA is 40 kilonewton meter, and I had considered it to be in the clockwise direction. So from here it is clear it is 40 kilonewton meter in the anti-clockwise direction. Right, moment at A is minus 40 kilonewton meter or 40 kilonewton meter in the anti-clockwise direction. In the anti-clockwise direction. This is done. Now simply on the entire structure you apply summation of Fy is equal to 0. From there you can write Ay plus Cy is equal to, what is the total length? 6 meters. 6 into 20. So from here Cy is 120 into, sorry, Cy is already calculated. So Ay is 120 minus 80, which is 40 kilonewton. So Ay is 40 kilonewton. So you have all the support reactions. Ay is 40, Cy is 80 kilonewton, and moment is minus 40 kilonewton meter. So support reactions are done. Now you have to draw its bending moment diagram. This being the structure, you have this. Now I want to draw its bending moment diagram. So let's start. I will neatly draw it here. Upward reaction of 40, moment of 40 kilonewton meter, and upward reaction of 80, and UDL of 20 kilonewton meter. So first I'll write the moment equation here for this portion. Let this be section 3.3. Okay. In this portion, beyond this internal hinge, let this be section 2.2, and let this be section 1.1. So for section 1.1, let the moment be m1. What will be the moment reaction be? At support A, there is a vertically upward reaction of 40. So 40 into x minus the moment is in, sorry, the moment is in this 40 kilonewton meter is in anti-clockwise direction. So minus 40 minus the load is 20 into x square by 2. X is being taken from the left hand side in this direction. So you can simplify it and write 40x minus 40 minus 10x square. Now write the equation M2. For M2, what will it be? You can write the equation of M2, or let's write the equation of M3. It's easier at this stage. So M3 will be, so it's basically an overhang. So it will be minus W, which is 20, into X into, it's CG, which is X by 2. So it is minus 10x square. So now I'll be drawing the bending moment diagram. So in the right hand side, it's an overhang. So, and the equation is minus 10x square. So it will look somewhat like this. In the middle, there is a hinge. This is A and this is B. And in the equation M1, if you put the value to be 0, you get a value of minus 40. So 40 kilonewton hogging. At P, the value will become 0. And in M3, if you put, for writing M3, you had taken x from this direction. Here, if you put x is equal to 0, that is the at free end, the moment should be equal to 0, and the equation is giving it to be 0, so it's correct. And at the support C, it is 2 meters away. So in the equation M3, if you put x is equal to 2, again you get 40 kilonewton meters minus 40. So again, this is hogging. So This is negative and negative. This value is 40 by EI. Since I'm drawing the M by EI diagram, this is the M by EI diagram, and this value is also 40 by EI. EI being constant, I've simply divided the diagram throughout by the EI value. Had the EI value been varying, which we'll see in a question after some time, then uh, you'll have to keep that in mind as well. So now draw the conjugate beam. So first draw the loading. This is being the load. So negative. So load is the loading is bending moment diagram is negative. So load is in the vertically upward direction. And in the real beam, the end D, here you can see end D, it is a free end. So here it becomes a fixed end. End A is a fixed end, so it becomes a free end. Point C is an internal hinge. So point C is a roller, so it becomes an internal hinge. And B is, we should have not have drawn it here. This is an internal hinge and this is a roller. So this is A, B, C and D. And what do you have to calculate in this question? You have to determine the deflection at point B. You have to calculate the deflection at point B. So deflection at point B in the real beam is equal to the moment at point B of the conjugate beam. So simply if you find the moment at point B, you can calculate it. You can calculate the deflection at point B in the real beam. So deflection at point B in the real beam is equal to moment at point B in the conjugate beam. So, how will you calculate the moment at point B? Take x from this direction. So, the section will be here about point B. The section is about point B. So at about point B, you'll have to calculate the moment. So here we already know when and what is the shape here. The bending moment diagram. The bending moment diagram in this region, it's a quadratic equation. So when this length is B, this height is H, then the CG will lie at X bar being equal to B by 4, and the area will be equal to BH by 4. Okay, so what will be the moment B? It will be, how much is this height? This height is 40 by EI. So the moment will be BH by 4. So 40 by EI into the base being 2 meters. Sorry, the area is BH by 3. I'm very sorry. It should be BH by 3. So this is HB by 3, and the lever arm from the left hand side it is at B by 4. So this will be 2 minus 2 by 4. So it is basically 80 by 3 EI into 3 by 2. So it comes out to be 40 by EI. So this is the moment at point B in the conjugate beam. So the deflection at point B in the real beam is 40 by EI. And how will this beam deflect? You can draw its deflected shape. This part will go like this. This part will go like this. And this part will go like this. So the deflection is in vertically downward direction. So the deflection is this much in the vertically downward direction. So this question is done. So moving on to the next question. So the question reads that you have to calculate the displacement and slope at point B in this figure. This is not point B. This is point B and this is point C. So you will have to calculate the displacement and slope at point B in this figure, and EI is the value of E is constant but I is varying. So E is constant for the entire beam. So first you will have to draw the bending moment diagram, and you can for that you need to calculate the support reactions. So here I will use the method of superposition and draw the bending moment diagram. I'll simply split this structure into two structures. On one structure, the vertical load will act, the vertical load of 20 kilonewton, and on one structure, the moment of 5 kilonewton meter will act. And then I'll combine their uh, bending moment diagrams. You can do it separately like this, or you can do it at once. So it's your wish. Uh, so this is the structure. I will break it into so on one structure there will be a load of 20 kilonewton, and on the other there will be a moment of 5 kilonewton meter. We know in this is clear. This is a symmetrical structure. This length is 2 meter, this length is 2 meter, load 20 kilonewton is acting at the midspan. So this reaction is 10 kilonewton and this reaction is 10 kilonewton. And what will be its bending moment diagram. Its bending moment diagram will look something like this. Point load is acting, reactions are like the reaction at the left support is 10 kilonewton. So at section here, what will be the bending moment equation? It will be 10 into x, x being taken from this direction. So here, this is the moment diagram. And what is the moment value? 20 kilonewton. So 10 kilonewton into the distance, lever arm 2 meters. That so a moment of 20 kilonewton meter is acting at the midspan. So for this bending moment diagram, I want to draw the M by EI diagram. So on the left, A to B, the moment of inertia is 2I, and B to C, the moment of inertia is I. So that should be kept in mind. So in the left portion, it is 2I. So 20 divided by 2EI. So it becomes 10. So 10 by EI. And in the right hand portion from B to C, the value of moment of inertia is I. So 20 divided by EI. And the load is, bending moment diagram is positive. So load is acting in the vertically upward downward direction. This is 20 by EI. And this will be the loading. Let me draw the conjugate beam here itself. So if this is the conjugate beam, this will be the supports. Fine. Now repeat the same exercise for this beam. What will be the support reaction? A moment of 5 kilonewton meter in the clockwise direction. So the support reactions must create a couple in the anti-clockwise direction, and the value will be 5 divided by 4. What is 5 divided by 4? 1.25 kilonewton, and this is 1.25 kilonewton. Then what will be the bending moment diagram? It will be this portion. It is vertically downward reaction 1.25. So it is creating a hogging moment of 1.25x, the section being taken at a distance x from the left support. So, and here from the right, if you take from the right hand side, the reaction is in the vertically upward direction. So the moment is 1.25x, x being taken from this side, and this moment is in the, it's creating a sagging moment. So the moment is positive and this moment is negative. And how much is this moment? 2.5 kilonewton meter. Now this will be the load in the conjugate beam. Moment is positive, so load will act in the vertically downward direction. So this is 2.5 divided by EI. From B to C, the value of, let me draw write ABC here, A, B, C. In the portion BC, the moment of inertia was I, so M by EI directly you can do. And in this portion, the moment is negative, so the loading is in vertically upward direction. And here, the moment will be 2.5 EI, 2.5 divided by 2 EI. So this is nothing but 1.25 divided by EI. And so on the conjugate beam, if the real beam is this, on the conjugate beam, both these loads will act. And the resulting displacement at point B, the resulting like we have to calculate the displacement at point B. So the resultant moment at point B in the conjugate beam will be equal to the displacement at point B in the real beam. So let this be the conjugate beam. Let this vertical reaction be RA. Let this be RB. And suppose, okay, let this be. Now I want to calculate, finally I'll have to calculate the moment and shear at point B. So to avoid confusion, let's take this to be C. This being point B, this is just a point. So first I want to calculate the support reactions. So RA plus RC first time, and the loading comes from here and here. So first I'm summing up the forces in the vertically upward reaction. Summation of Fy is equal to 0. Ra plus Rc is equal to, now first referring to this portion, this is first portion, this is first loading and second loading. First referring to the first loading. So from there you can write half the base being 2 meters into height. First term is 10 divided by EI plus the second triangle half into base into 20 by EI. Okay, and this comes from the first loading, and from the second loading it is half, again base is 2 into 1.25 EI. Y minus the load is in the vertically upward direction. So if I want to maintain the sign convention, RA in the vertically upward direction, so positive, RC in the vertical upward direction, so positive. Loading from A is in the downward direction, negative. So this is negative, this is negative. This part 1.25 EI, this triangle, this is in the vertically upward direction. So I've taken it to be positive. Again, negative half into base into 2.5 divided by EI is equal to 0. So from here you get RA plus RC is equal to 26.25 EI. This is first equation. Then you take moment about point C is equal to 0. So in this structure, you make moment about this is C, this is A. Moment, you take moment about point C. So RA into 4 plus half into 1.25 divided by EI. So RA into this distance is 4. RA is in the vertically upward direction, so RA into 4. Now the effect, you are considering the effect of the second loading first. So in this highlighted portion, this pink portion, this will create a moment about point C. In this load will create a moment in the clockwise direction. So the sign is positive. Half base into height, this gives the total moment into the lever arm, which is 2 plus 1 by 3 into 2. Fine. Now take the contribution of this part. This will create a moment in the anti-clockwise direction. So it will be negative. So it is minus half into 10 by EI into 2 into 2 plus 2 by 3. This is done. Now take this first loading diagram and now the load is in the vertically downward direction here as well as here. So about point C, it will create a moment in the anti-clockwise direction, means here both the moments will be of the negative sign. Minus half into 20 divided by EI, half base into height into lever arm 2 into 2 by 3. This contribution is coming from this triangle, and CG from the point C here from this side. How much is the CG? This length is 2 meter, so it will be 2/3 of that length, so 4 by 3. And for the second triangle, it is half into 10 by EI into 2. Wait, I like to check the values. 1.25 EI I have considered. This 1.25 is coming from this triangle, from the loading pattern 2. So first I'll write all the terms from the loading pattern 2. So minus half into 2.5 EI into 2 into the lever arm, which is 2 into 2 by 3. Fine. Now I'm writing all the terms from the loading pattern 1, which is half into 10 by EI into 2 into 2 plus 2 by 3, and another term is half into 20 by EI into 2 into 2 into 2 by 3. This again is lever arm. This is equal to 0. So from here you will get RA is equal to 40 by 3 EI, and from here you will get RB. Use this equation that RA plus RC is 26.25. Okay, 31.25 EI, summation of forces. Okay, this equation, let me check. Half into base into height, half into base into height in the downward direction, so it is negative. This is in the upward direction, half into base into height plus half into base into height. So this is cancelled, this is cancelled, this is cancelled, this is cancelled. So 1.25 minus 2.5 minus 10 minus 20. Right, it should be 31.25. Thank you for correcting the mistake. It should be 31.25. So here please calculate the value of RA and tell me what should be its value. Is the value 40 by 3 EI correct? This is correct. It should be 40 by 3 EI. Fine. So what will the value of RC be? RC will be 31.25 EI minus 40 by 3 EI. So its value should be 31.25. It should be 17.92 divided by EI. So RA and RC have been calculated. Support reactions have been calculated. Now what do you have to do? You have to calculate the moment at point B and the shear at point B in the conjugate beam. Once you get the moment at point B, that will be equal to the deflection at point B in the real beam, and the shear at point B in the conjugate beam will be equal to the slope at point B in the real beam. So calculate moment at B. So what will the value be? The reaction at RA is 40 by 3. So 40 by 3 EI into this being the structure. 40 by 3 EI is the reaction RA, and the point B is at a distance of 2 meters. So RA into 2. So 40 by 3 into 2, done. Now calculate the effect from the loading diagram 2. So that will be half into base into height is 1.25 EI into 2 into 1 by 3, done. And from the loading 1, that is half into base is 2 into height is 10 by EI into 2 into lever arm. So on calculating this, you will get to be it is 20.83 divided by EI. Now you will have to calculate V at B. What is the shear at B? For shear at B, simply calculate triangular loads are there. Simply take the load. It will be, the reaction is RA is 40 by 3 EI plus half into base into height, which is 1 by 25 EI minus half into base into height 10 by EI. So you can calculate this. This will be 40 divided by 3 plus 1.25 minus 10. So that will be 4.583 by EI. So this will be the deflection at B in the real beam, and this will be the slope at B in the real being. So now in this question, it is given that the flexural stiffness of this L-shaped frame is EI, and you have to determine the horizontal displacement of the joint C, and here you will have to use the unit load method. So in unit load method, here question number 5. Do you want to look at the question or at any particular position in the solution?
I want to see the solution. Okay. Madam, slightly downwards.
You can take the screenshot.
1 minute, 1 minute. I'll take. Yeah. 1 minute. Yes.
So cool, it's done.
Yes, yes, yes.
So in this question, you will have to use the unit load method and you'll have to calculate the deflection at joint C. So in unit load method, so basically under the given loading conditions, draw the bending moment diagram, and uh, the logic of the idea behind the unit load method was already covered earlier. So here I'm just listing down the steps now, that what do you need to do. First, under the given loading, calculate the bending moment diagram. And since you have to calculate the horizontal displacement at joint C, simply apply a unit load at point C in the horizontal direction. Whether you want to apply it from horizontally left to whether you want to apply the load in this direction or in this direction, it depends upon you. You can do whatever you want, and if you assume a load in this direction and the on subsequent calculation the deflection is positive, means actually the deflection is happening in this direction. Or if it's in the opposite direction, if you get a negative value, it means the deflection is taking place in the opposite direction, opposite to the loading direction. So here I want to calculate the horizontal displacement at joint C. So first simply I am drawing the bending moment diagram, or simply I am writing the moment equations here. So let here the moment, let me take a different color. Here let the moment be M1, and here let the moment equation be M2. So M1 in the clockwise direction plus this moment 1 is equal to 0. So the moment here is minus 1 kilonewton meter. And in this portion 2, M2 in the clockwise direction plus the load is 0. Wx square by 2. Wx square by 2, okay, x being taken from this direction, Wx square by 2 plus this 1 kilonewton meter moment. This is again in the clockwise direction, so 0. So m2 is equal to minus 1 minus 0.2x square. So these are the two moment equations, this and this. So when this is done, okay, then take the structure and apply a unit load in this direction. Fine. Again, I'm taking x1 from here. Actually, here x1 was from this direction. You did not need it. And this was x2. So let me write this x2 and this is x2. Let here the moment be m2, here the moment be m1, and x2 be taken from this direction. And this height is 8 meters and this span is 10 meters. Fine. So here again m1 is this moment plus x1. There is a unit load of 1 in this direction and lever arm is x1. So again in the clockwise direction. So m1 is equal to minus x1. Done. And m2 again in the clockwise direction plus, see how much this moment is being created, plus 8 in the clockwise direction, 1 unit load and the lever arm is 8 meter. So m2 plus 8 is equal to 0. So m2 is equal to minus 8. Now simply use the unit load method that says delta is equal to integration. Simply plug in the values. Now since there are two beams, you will have to carry out this operation over. There are two members in this frame. You will have to carry out this integration, or you will have to sum the results uh, from these two structural members, that is AB and BC. So this BC, the length is 8 meter. So you will have to integrate it from 0 to x, 0 to 8. And this x starts from here. So you have to integrate from 0 to 8. There m1, this is minus x1. And from here it was found to be minus 1 by EI. EI is same for both the beams, both the structural members, EI into dx, and for the other member the length is 10 meters, so 0 to 10, here it is minus 8 into this expression, which is minus 1 minus 0.2 x2 square dx2 divided by EI. So let's solve this. So 0 to 8, this is 1 by EI x1 dx1 plus 0 to 10. This is 8 into 1 plus 0.2 x2 square dx2 by EI. Now this will be 1 by EI x1 square by 2. You put the values, then this should be 8 by EI, and here it is x2 plus 0.2 x2 cube by 3, and you put the values 0 to 10. So here it will be 1 by EI into 64 by 2 plus it is 8 by EI. 10 minus 0 is 10 plus 0.2 into 1000 by 3. So on simplifying this, it will be it will be 1936 by 3 EI. So this is the deflection. And it turns out to be positive. It means that actually the frame is moving in this direction. Okay. Now moving on to the next question. This is again on unit load method. You will have to calculate the vertical deflection at D. So for that, again, you will have to write the moment equation for all the members. So for that, first I'll calculate the support reactions. So here, let this be AY, this is AX, this being roller, there will only be DX. Let this moment be, this being the M1, this be M2. Let them, like, I'm naming the moment equations. Okay, M3, okay, done. Simply take the moment about point A and make it to be 0. So the contribution of AX, AY disappears. So you can calculate dx from here. Dx into 8 plus 0.1 into 10 into 5. So dx is equal to 5 by 8 and summation of fx is equal to 0. So ax plus dx is equal to 0. So ax is equal to minus 5 by 8. So summation of fy is equal to 0. So from there ay minus 0.5 into 10 minus 0.1 into 10 is equal to 0. So ay is equal to 1. So from here I can write m1 is 0 because no horizontal, no vertical shear or vertical reaction. So m1 is 0. m2 is equal to, this dx will create a moment in the anti-clockwise direction. So that is equal to 5 by 8 into x2. See, x1 is from this side, x2 is from this side, and x3 will be from this side. So, and m3 is equal to, what will m3 be? M3 is equal to this. I'll not write it from this side, x3. I'll take x3 from this side. Just ay. Ay is 1. I can write it like this. What will be easier? Okay, let's write it from this side. Let's maintain it. M3 will be, how much is dx? 5. M3 in the clockwise direction, positive. Dx is creating a movement in the anti-clockwise direction. Okay, M1, M2, M3 not understood. See, M1, this moment is in the, I'll write down the equations again. See, uh, M1 moment in the anti-clockwise direction. So I'll write it as minus M1. And you are taking X from the support. This X1 is from the left hand side. Basically here the portion is, you are, this is D, this length is X1. Here the moment is M1. You have a shear, let's say V1, and the support reaction is dx. What will the value of M1 be? It will be 0 because there is no vertical shear or vertical force to create moment. So M1 is equal to 0. Is M1 clear?
Okay, means capital M means moment at any section when all the loads are applied, and small m means remove the external loads and apply new load. Correct, na?
Right. Here, okay, you're confused because of the nomenclature. Here, simply I'm calculating the moment because of the external load.
Okay, okay,
Here, if you are considering small m to be because of the external load, it should be small m1, small m2, small m3.
okay, okay.
Okay.
Moment due to unit load, that is.
Moment, here I'm calculating moment due to external load because these support reactions were because of this UDL, right?
Okay, okay,
Then I'll apply a unit vertical load at support D and calculate the moments. I've not done that till now.
okay, okay, okay.
Mhm.
So,
So M1 is done. So now for M2 again, basically I'm cutting it like this. So this is M2, this is dx, and this x2 I'm taking it from from this end. So again there will be a force V2, and for this let this point be x. I am taking the moment at x to be 0. So this contribution of V2 will disappear. M2 is in the clockwise direction minus dx, and this dx is at a distance of x2. So this into x2 is equal to 0. So M2, what is the value of dx? Dx was 5 by 8 here. So plug in the value. 5 by 8 into x2. So this is calculated. So M3, for calculating M3, you cut a section from here. So start from here, go like this. This is a straight line. Okay, this is a straight line. Consider it to be a straight line. A unit load is acting here. Sorry, not unit load. This UDL is 0.5 kilonewton meter. This moment is M3, shear V3, load dx, support reaction dx, and from this length, this side, this length is x3. So M3, moment in the clockwise direction. This load is also creating moment in the clockwise direction. So 0.1 into x3 square by 2 minus dx into 8. This height is 8 meter. This is equal to 0. So M3 is dx is 5 by 8. Let's plug the value here. 5 by 8. So this value is 5 minus 0.1 by 2 x3 square. So this is done. Now we'll apply a unit load at point D, and we have to calculate the vertical deflection at point D. So I'll apply a unit load in the, let's say, in the vertically downward direction. So I have a pin support at the top and a roller support here. So I have a pin support here, a roller support here, and I am applying a unit load in the vertically downward direction. So under this external loading, first I'll calculate the support reaction. This being dx, this is ax, this is ay. Done. So let me use a different nomenclature here. Let this be small m1, let this be small m2, let this be small m3. Fine. So here we can see ay is equal to 1. This is clearly visible. Summation of force in vertically upward direction is 0. So ay is equal to 1. Then summation of ax and dx is equal to 0. So do you need the vertical reactions? Yes, you need. Ax plus dx is equal to 0. Now here take moment about point A to be 0. So about that, from here dx is equal to 0. So ax is also equal to 0. So small m1, that moment, here you can write that m1 So this 1 kilonewton which you are applying at support D, it is basically generating a hogging moment. So M1 is equal to minus 1 kilonewton meter. You just imagine this portion. This is M1 and you have a vertically downward load of 1 kilonewton, and this is X1. So you have a hogging moment of minus 1 into X1. So minus X1. Next, you have to calculate M2. M2 will be, you take it like this, This is M2. This much is X2, and this is 1. This length being 10 meters. So M2 will be M2. So this is M2 in the clockwise direction. So plus M2, and this 1 kilonewton is creating a hogging moment. So 1 into 10, that is 10, is equal to 0. So M2 is equal to 10 kilonewton meter. And finally M3. So from here you have X1. From here you had X2, and from here you have X3. So next I will calculate M3. So M3 is, you take this portion, and this portion. You have a vertical load of 1 kilonewton. This is 10 meters. This is 8 meters, and this is M3. You do have shears at this point, V3, V2, and V1, but I'm taking moment about that section where I'm cutting, so the contribution of V3 is disappearing. So M3 is clockwise moment, so positive minus 1, and how much distance is it away from here? If this length is x3, this distance is 10 minus x3, so this is 10 minus x3 is equal to 0. So M3 is equal to 10 minus x3. Done. So now use the unit load method and integration. Here I should write M from the external load, that structure, divided by small m, small m. So just when you plug in these moment values, finally you will get deflection to be equal to 1225 by 3ei. And when you substitute the value of E and I, you will get it to be equal to 245 mm. So is this method of calculating the moments, and this I have not explained further because simply you will need to plug in the values and carry out the integration. But writing down these values of M1, M2, M3 in this structure as well as in this structure, is that clear? Okay, I'm assuming it's clear. Finally, the last question here, a very simple question, but a fundamental question. Here again, the bending moment diagram is given, and I want you to select the option which is the correct beam with the loading as well as the supports. So, this is the bending moment diagram. So, which one is the correct answer? So, the best way, okay, option A. So, the best, yes, A is the correct option. So, the best way to visualize it is to draw the deflected shape. How will this deflect? This will deflect like this. This will deflect like this. This will again deflect like this. And this is a fixed support. So it will move like this and this. So you can simply remove option D because at this support moment exists and here the moment is 0. So you can remove D. Now you can also remove C because how will C, a unit load is acting. So what will be the order of the bending moment diagram? It will be a linear uh, line, means it will be of the order 1. So and here the bending moment diagram is curvilinear. So that can't be the option. So you can remove C. Now for B, how will the moment, nature of bending moment change here from here? So even B is not possible, and A. For A, this might be the probable. If these, even this portion in the curvilinear portion, this portion, it can be a quadratic equation. Then this can be the bending moment diagram. So A is the correct option. So this is the correct option. For C, the bending moment diagram will be of something of this sort. Since it is a point load, it will be something of this sort. For C, this is the bending moment diagram. For D, if I show you, the bending moment diagram will be D, this is a fixed support. So the bending moment diagram will start from here, then it will move up and it will be something like this. So even D can't be the correct answer. How will the bending moment of B look like? B will something look like this. The bending moment is always sagging. So it will look like this. So is this question clear? Okay. If you have any other doubts, you can ask me. Any doubts regarding what I've covered in this session? Okay, for ILD, it will be on next Tuesday. Okay. Any other questions? Okay. Then thank you for attending the session. If you have any other doubts, you can mail me. This is my email ID. This is my email ID. You can mail me and ask questions. So thank you. I'm closing the session. Let's meet again next week. Thank you. I'm closing the session.